Hello, my name is Carlos Jerónimo Zárate, and this is the presentation of my final course report about emotional speech analysis. I've done this project with my two classmates, Miguel and Carlos. So first of all, I have to say that this is a project based on speech analysis that is a cutting-edge technology nowadays. It's based on a Kaggle competition about using the roughest dataset, Riverstone audiovisual database of emotional speech and song. And we will be performing some deep learning tools and techniques in order to complete this project. Main objective of this report is to see how to detect emotion directly from speech. We're using the roughest dataset that was initially thought for audio and video tasks. Also, we are using just the audio files here. The final task will be to classify each of the audio files in the emotion that the different people say in this statement may be feeling. First of all, we want to know how our dataset is. Kaggle gives us a list of 24 directories which represent the 24 actors that we have. Each directory contains 60 different files of speech corresponding to that actor. That is just a portion of the roughest dataset. We know that the roughest dataset contains both speech and song and audio and video files. Here we will be using just the speech and audio ones. This portion of the roughest contains 1,440 files, a total of 24 actors and 60 trailers per actor. The roughest contains 24 professional actors, 12 female and 12 male, vocalizing two lexically matched statements in a neutral North American accent. Speech emotions include calm, happy, sad, angry, fearful, surprised, and disgust expressions, a total of 7 different emotions. Each expression is produced at two levels of emotional intensity, normal and strong. Each of the 1,440 files has a unique file name. The file name consists of a 7-part numerical identifier. These identifiers define the stimulus characteristics. Here we can see what these identifiers represent: modality, vocal channel, emotion, emotional intensity, statement, repetition, and actor. After charging the data, we are going to see the main activities that we have to develop. First of all, we have the exploratory data analysis and feature extraction, where we will work in our dataset. Then we'll build a first model based on a one-dimensional convolutional neural network model. Then we will try to improve the performance of this model using data augmentation. And finally, we will end with by trying a new model using a two-dimensional convolutional neural network architecture. So, here we have a table with the different classes to be trained. We have seen that the researchers suggest to differ male and female audio files while training in order to improve the model's performance. We define these two classes in this table. Here we've got 7 different classes for female for each of the sentiment and 7 different classes for male. Then we will use a feature known as MFCC. It is proved to be one of the best for this particular problem. MFCC is well known to be a good feature for classifying speech and audio of human voice. It stands for male frequency substrate coefficient, and it is a very good representation of the vocal tract that produces the sound. The most common machine learning application treats the MFCC itself as an image and becomes a feature. The benefit of treating it as an image is that it provides more information and gives one the ability to draw on transfer learning. This is certainly legit and yields good accuracy. However, research has also shown that statistics relating to MFCC can carry good amount of information as well. We will be using both in this project. Also, we can see the shape of an MFCC output here. It's a 2D matrix representing the MFCC bands over time. To simplify things, what we're going to do is take the mean across each band over time, in other words, row means. So if you look at the MFCC plot, the first band at the bottom is the most distinctive band over the other bands. Since the time window is a short one, the changes observed over time does not vary greatly. The key feature is capturing the information contained in the various bands, so we have plotted the mean of each of the band and display it as a time series plot to illustrate the point. There, the angry female and angry male for the same sentence uttered are represented. So, for the same sentence being uttered, there is a clear distinct difference between male and female, in that female tends to have a higher pitch. We proceed with our first model. We normalize our data and split it to train this model. We can see that the loss starts to plateau around 125 epochs. We could keep it at 125 as the final model. As it can be seen, it has a global accuracy of 53%, which may seem low, but considering that a random guess correct is 1 out of 14, which is 7%, it is a really good performance. For gender differentiation, we obtain a 95% of accuracy, and we can see that the model's performance is really good in this classifying by gender. And finally, we can see the pure sentiment classification, and we've got a 55% of accuracy, which is still not bad. After that, we try to improve those scores by performing data augmentation. We use some techniques of data augmentation to increase the material for the training, and we will compare the final results with the previous we obtained. We used various augmentation methods in order to expand our dataset. Those are adding static noise in the background of the audio files, shift, that consists in moving the audio randomly to either the left or right direction within the fixed audio duration, stretch, that consists in stretching the audio so the total duration is longer. This introduces an effect of slow motion, pitch, that works accentuating the high-pitched notes by normalizing the file, dynamic change, that only increases the frequencies reached by the signal, and finally the speed and pitch method, which dramatically alters the audio in many ways. It compresses the audio wave, but keeping the file total duration. Its effect is opposite to of the stretch augmentation method. So, after augmenting our data and following the same process we did in the previous slide, we've got a results of global accuracy of 67%, which is much better than the one we had before. We've got a gender accuracy that is a bit lower, but it's no problem. And final emotion accuracy of 69%, which is actually pretty good. Finally, We'll try a 2D two-dimension CNN model. This model takes in a 2D array of 30 MFCC bands by 216 audio lengths as input data. So we can just imagine it as a 30 per 2016 pixel image. It's got 4 convolution blocks of batch normalization, max pooling, and debug node. So our standard setup is similar to VGG19, just not as deep. We are using EDA and Feature Optimizer. So we've seen the visualization of the MFCC, where it captures all the core information of the audio file into a single image. While if an audio information can be interpreted as an image, then surely we can apply the same image recognition approaches like in VGG19 or ResNet. So we use the entire MFCC data and treat it as an image and push it through to a 2D convolutional neural instead of 1D convolutional neural network that we saw in the previous slides. This will be without the documentation for a first try. Instead of letting it run 200 epochs like in the previous model, we will be using just 100 epochs, because the convergence is very quick in this case. We obtain an overall result of 74% of accuracy. This is much better than in other experiments. We can see the power of MFCC and 2D CNN models. So this model is much better than all the experiments we did with the one-dimensional convolutional neural network, and even without the documentation. As future work, we'll leave the job of using the data augmentation techniques introduced in the previous slide. This for sure will improve drastically the accuracy and performance of our model. Learning outcomes have improved the skills on several fields like acoustic treatment and different types of techniques, deep learning for audio, expanding our knowledge on deep learning applications, and future presentation scenarios in order to adapt a more fluid speech for a better understanding. Thank you very much. This is all.